In this first video for section 8.5, we are going to look at using partial fractions with linear factors to integrate. So we're going to be looking specifically at how partial fractions can be helpful when we're trying to integrate. For instance, let's say I want to integrate 1 over the expression of x squared minus 5x plus 6 dx. Now, if I did not have partial fractions as an option, I would have to complete the square and then use trigonometric substitution to integrate with respect to theta. And then I'd have to back substitute to find the solution with respect to x, which, as we remember from our last video where we had to do all of that, is kind of a lot of work. So instead, I can use partial fractions to rewrite the integrand as a much simpler version. And I know that once I have it in this form, I have a pattern, the natural log pattern, that says my solution is the natural log of x minus 3 minus the natural log of x minus 2. Obviously, both are absolute valued, plus c. And so that's really super easy. So instead of doing it the long way, let's talk about how to do it the short way. And again, I'm going to pretend that you've never ever done partial fractions before. So I'm going to take you through how to write it like this, because obviously integrating once we got to that point was very easy. So let's talk about partial fraction decomposition and how it works. The first thing you should do is rewrite your denominator as factors. So this would be x minus 2, x minus 3. And again, the actual first step, which we don't have to do here, would be if I have an improper fraction where the numerator degree is greater than the denominator, I would first do long division, and that would leave me with a polynomial, which is easy to integrate, and then some fraction left over, and then I would use the fraction, obviously, for partial fraction decomposition. In this case, I just have 1 over x minus 2, x minus 3. I'm going to leave myself a little bit of space, and notice I'm not writing the integral because I'm just going to do all of the work and then plug it back into integrals as I did here. So again, I'm going to leave myself some space. I'm going to take a over my first factor, and it doesn't matter which one's which, leave a little bit of space, and then write plus b over my second factor. And again, typically I wouldn't show as much work as I'm going to show on this slide because I'm just assuming that you've never seen a partial fraction before, so we're just going to walk through it like you've never done it before. What I'm going to do is I'm going to take every single fraction times x minus 2 times x minus 3. So x minus 2 times x minus 3, and again, I typically wouldn't show this. I'm just showing you so you can see exactly what's going to happen. So as we can see, I would then end up canceling all of my factors on the left side, leaving me with 1. And on the right side, I would end up with x minus 2 canceling, which gives me a times x minus 3, and x minus 3 canceling, which leaves me with b times x minus 2. Now from here, there are actually kind of two trains of thought, two ways to think about this, and we're going to do it the easier way. So the easier way says, hey, I've got this equation, and I'm just going to make up a value for x. Any value you want, but obviously we're going to use values that are going to make it easy for us to solve. So for instance, if I look at using a value of 3, then that would give me 1 equals a times 3 minus 3 plus b times 3 minus 2. 3 minus 3 is 0, so I still have 1 on the left side. A times 0 is 0, so that gives me b times 3 minus 2, which is just 1b. So b is 1. Then I would choose a value of 2. Choosing a value of 2 gives me 1 equals a times x minus 2. I'm sorry, 2 minus 3. Got confused for a minute. 2 minus 3 plus b times 2 minus 2. 1 on the left side. a times 2 minus 3, 2 minus 3 is negative 1, so that's negative 1a, plus b times 0, dividing by negative 1 gives me that a is negative 1. So now that you have solved for a and b, that is when we can go back and rewrite our expression using those two values. So if I go back to this step, I know I've got kind of a mess going on, but if I go back to that step, I have, that was a horrible circle, I have that this expression, which is what I have on the left side, is equal to a over x minus 2 plus b over x minus 3. So now I can rewrite that my expression is equal to a, which is negative 1 over x minus 2, plus b, which is 1 over x minus 3. So let's take a look now at this result. Do you see that I had positive 1 over x minus 3, and I had negative or minus 1 over x plus 2. So that's exactly where that came from. So I can rewrite my integral then as the integral of, and I'll just keep it in the same order that I have it here, 1 over x minus 3 dx minus 1 over x minus 2 dx. Again, that was using partial fractions. And we've already gone through the answer for that, so we don't even need to continue. All right, let's take a look at another question, and on this one we're actually going to have a repeated factor, and we're going to talk about how that changes things. So just as I did before, the first thing I should do is factor my denominator. So I didn't have to divide again on this one, but if I factor, I end up with x minus 2 times x minus 2, or x minus 2 quantity squared. And so I can see, obviously, that I have a factor that occurs more than once. X minus 2 occurs twice. So that will change a little bit as to how we write it as partial fractions. So I'm going to rewrite the left side, which is 5x minus 2. And again, when I'm doing the partial fractions, I don't have to write the integral. So this is x minus 2 quantity squared. And I'm going to write a over the factor one time. This is how we deal with multiple factors that are the same. And then b over the factor squared. From here on out, everything is the same. So I'm going to take everything multiplied by x minus 2 quantity squared over 1. My first fraction, the x minus 2 quantity squared, would cancel completely, leaving me with 5x minus 2. For my second fraction, one factor of x minus 2 would cancel, leaving me with a times the remaining factor of x minus 2. And then for my third, I get plus b, because x minus 2 would cancel completely. So just as I did on my last example, to solve, I can start by letting x equal any number that I want. So if I let x equal 2, and I'm choosing 2 obviously because of how it works with a times x minus 2, I would get 5 times 2 minus 2 is equal to a times 2 minus 2 plus b. 5 times 2 is 10 minus 2 is 8. A times 2 minus 2 is 0a, or just 0, and then equals b. Now from here, obviously I want to solve for b, but there's no number that I can plug in for x to just magically solve for b. So I have two choices. My first choice is to let x be any other number that I want it to be. So not 2, but something else. And I'm going to then just plug it in. 5 times 1 minus 2 equals a times 1 minus 2. And then instead of b, I'm going to replace b with 8 because I already know that b is 8. So now I have 5 minus 2, which is 3. I have a times 1 minus 2, so I have negative a plus 8. And I end up with, subtracting 8 from each side, negative 5 is negative a, so positive 5 is positive a. So that's probably the easiest way to go about it. The other way, and I do want to introduce you to this way because A lot of people, when they solve partial fractions, do it all in this method, so I just want to point out that this is another method that you can use. If I took this guy and rewrote it, 5x equals, and distributed the ax minus 2a plus b. Oops, I forgot my 5x minus 2. Let me start that again. 5x minus 2 equals all of that. The other way to think about this is you've got all of the values that have an x, and then you have all of the values that don't have an x. And so I can think of this as 5x minus 2 is equal to ax, and then I've got plus negative 2a plus b. And the reason I'm bringing this up is, again, I now have an equation that I can solve. If 5x needs to equal ax, then obviously 5 equals a. Or if negative 2 must equal negative 2a plus b, where b is already known to be 8, then I can subtract 8 from each side, divide by 2 on each side, and end up with 5 equal a. So again, just another way to think about partial fractions. Hopefully that all made sense to you. No matter what, we have our solutions now. Or not our solutions, we have our new integrals now. So I'm going to integrate. I'm going to use this expression and replace a with 5. So 5 over x minus 2 dx. And then plus b, which is 8, over x minus 2 quantity squared dx. And now I'm just going to integrate all of that. So I'm going to move this guy out of the way just because he's annoying and in my way. If I integrate my first expression, my first integral, and I should probably not forget to put an integral on my second expression. On my first expression, I would get 5, and then I'm integrating 1 over x minus 2, so I get the natural log of the absolute value of x minus 2. For my second expression, I'm going to think about u substitution. If u is x minus 2, du is obviously just dx, then I can rewrite this guy as the integral 8 times the integral of u to the negative 2 du. Therefore, if I integrate that, I'm going to end up with 8 times u to the negative 1 over negative 1. So that's going to give me minus 8, and then u to the negative 1, u was x minus 2, so u to the negative 1 is 1 over x minus 2 to, obviously, the first power, plus c. So my final solution, 5 natural log absolute value of x minus 2 minus 8 over x minus 2 plus c. This is the last example we'll go through in this video, so if you'd like, you can press pause and try this question on your own, and when you're ready, press play to see how you did. The first thing I would do is look at the denominator, x cubed plus 2x squared plus x, and I want to factor that. So I don't need to worry about trying to factor the numerator, but the denominator, I would first take an x out of everything, and then factor what's left over, which would give me x plus 1, or x plus 1 quantity squared. So that means my integral is now x squared minus 6x plus 2 divided by x times x plus 1 quantity squared dx. So now I'll start with the partial fractions, and of course this time I'm going to have 3 variables to solve for, a, b, and c. So if I have x squared minus 6x plus 2 over x times x plus 1 quantity squared, I'll have a over x, and then here's my repeated factor. Remember, with repeated factors, I write it just to the first power and then to the second power. And I could continue that for the third, fourth, fifth, etc. As I did before, I'm going to take everything multiplied by the denominator, which is this. For my first fraction, x squared minus 6x plus 2 is what I would be left with because the entire denominator would cancel. For a, only the x would cancel, leaving me with a times x plus 1 quantity squared. For b, I would have x and also x plus 1 because one of the factors would cancel. And then for c, I would just have the x. So to start, I'm going to do exactly what I did in my last example, which is choose a value for x that I think is going to be easy to work with, which of course would be -1. So that gives me -1 squared, which is 1, minus 6 times -1, so minus -6 or plus 6, plus 2, is equal to a times -1 plus 1, which is 0, so a times 0 squared, which is still 0. Plus b times -1 times -1 plus 1, which is 0, plus c times -1. On the left side, 1 plus 6 is 7, plus 2 is 9. A goes away, b goes away. I get -1c, so therefore c must be -9. So I have one of my values. I need to now find out what's going to happen with a and b. Well, what if I let x equal 0? And why did I choose 0? Because of cx. So I would get 0 squared minus 6 times 0 plus 2. I would get a times 0 plus 1 squared plus b times 0 plus 1 plus c times 0. So what am I left with? 0 minus 0 is 0 plus 2 is 2. On the right side, a times 1 squared is just 1a. No b's, no c's. So I have a equals 2. Now for our last one, remember I can just choose any value of x that I want. So let's let x be 1. And I'm going to write then 1 squared, which is 1, minus 6 times 1, which is 6, plus 2. A is 2, so 2 times, what did I say? X was 1, so 1 plus 1, so 2 squared, plus b times 1 times 1 plus 1, plus c times 1, and c is -9, so -9 times 1 is -9, or I'll just write -9. Sorry, I'm all shoved in the corner over here. 1 minus 6 is -5, plus 2 is -3. 2 times 2 squared is 8. b times 1 times 2 is 2b, and then of course -9. I would subtract 8, well I would add the 8 and -9 to get -1. Add 1 to each side, I get -2 equals 2b. Divide each side by 2, I get -1 is equal to b. So those are my 3 solutions, and obviously I'm out of room. So I'm going to rewrite this with a as 2, with b as -1, and with c as -9 on the next slide, and then we will continue our work for integration. The good news is we've already done all of the hard work. And so what I'm going to do now is just do any simplification that I can. So again, I've got 2 over x, or I can just move that 2 to the outside. So I end up with 2 times the natural log of the absolute value of x. And then same thing happens in the middle. I have minus natural log of the absolute value of x plus 1. And then just as we did on our previous example, I'm going to use u substitution for my last integral. And again, notice I've already moved the 9 to the outside on this one. So u is going to be x plus 1, which means du is just dx. And this integral can now be thought of as 9 times the integral of u to the -2. du, which means my solution is going to be 9 and then u to the -1 over -1, which makes this now a plus, and then u to the -1 would be x plus 1 as the denominator, plus c. Let's go ahead and simplify now anything that I can. So the first thing I see is I've got natural log for two different values, and whenever I have that, I should use the properties of logarithms to combine those. And so if you'll recall, first of all, if I have a 2, I can make that the natural log of x squared, and if I have subtraction, I'm combining by division. So this first boxed white value becomes the natural log of the absolute value of x squared divided by x plus 1. And again, that's combining, making the 2 an exponent and combining these with division. And then I'm just going to write the 9 as the numerator, so 9 over x plus 1, and then plus c. Up to this point, we've only looked at expressions that had linear factors, x to the first power. Now we want to take a look at what happens when you have a quadratic factor.